Thank you. So first, I want to thank ANERIS for the invitation and Friends Bioimaging for giving me the opportunity to present you a small discussion. So my presentation is not going to be as shiny as the previous two ones where we had very nice sequences, images, beautiful things. Here, my main goal is to give you an idea, try to give you the intuition behind machine learning, because we all use machine learning and deep learning on an everyday basis. Many tools that we use every day are based on this. Most of it, so some people, and here in the audience, some people might know what is behind machine learning. I'm not sure everybody knows. And so I think it's very important when you use these kind of tools to at least have an intuition about what is behind those very powerful methods. So let me start. I'm gonna first start with a brief history of deep learning. Deep learning arrived in 2011 for speech recognition, and if you use speech recognition algorithm, meaning Alexa, Google Assistant, Siri, all of these are based on deep convolutional neural networks. And 1 year after, they were used, these deep convolutional neural networks, for computer vision. And it was really a huge advance for computer vision, especially, so first for image classification, so to know if you have a cat, a dog, a person, a bike in an image. That really made a huge difference. What participated to the hype of deep learning, I would say, was when AlphaGo, so an algorithm that was trained based on still deep convolutional neural network to play Go game in 2016. And it made a huge noise because at that time, so the game of Go is very different from many other games, in the sense that you have an infinite possibility of moves. So compared to chess, where you have many moves, but limited moves. So you could think that if you can put all the moves in the memory of your computer, then you're going to always be able to know what move is the best, okay? Compared to what the other player is playing. The Go game, it's not possible because you have an infinite possibility of moves. And even in the community, many people in AI thought at that time that it was a bit too early and that wouldn't work. And actually, AlphaGo beat very badly Lee Sedol at the time. It was one of the best players in the world. And so it made a huge noise at that time. And then we cannot ignore all the work in natural language processing that really made huge changes with the advent of transformers in 2017. So first for translation, you might use DeepL, which is based on transformers. So started in 2017 and was really much more performant than the previous generation of translation algorithms. And of course, chatbots. Who hasn't heard about ChatGPT? It's hard not to hear about it. So transformers made a huge difference in natural language processing. They're also used in computer vision now, but I will only talk about deep convolutional neural networks to illustrate how deep learning is used in computer vision. Of course, the tech industry uses a lot of deep learning, but it's also used in art. You might have used DALL-E, which is also developed by OpenAI, where you have so it made a bridge between chatbot and images, so you can ask for you describe something like a small drawing, a sketch, or an image, and it's going to generate several images corresponding to what you are asking. Music, we all heard about the Drake deepfake by the Alta band, where so there was a song that came out with Drake singing, and Drake has to say it's not me because everybody thought it was Drake that was actually rapping. And data journalism, so with events like the war between Russia and Ukraine, we hear a lot about people that use data to do journalism. So it's everywhere. No, it's definitely everywhere. But what is artificial intelligence, and more particularly machine learning? So I'm going to start with, sorry, I'm going to remove this. Yes. So this is a usual sketch that people show when they talk about artificial intelligence. And basically, artificial intelligence doesn't mean anything. Whenever you use a computer to do an analysis, you can say it's artificial intelligence. Nobody can agree on what it is, but people agree that machine learning is part of AI, and deep learning, which is part of machine learning, is also part of AI. So here I showed a few methods. So for machine learning, we often hear about random forest or SVM. Deep learning, so I told you deep convolutional neural networks were a huge advance for computer vision and speech recognition. We have the transformers, of course, and several methods. So to talk about this, let's start by what is actually explicit programming. So I don't know if it's the right term, but if we want to process data in a way that is not machine learning, that's certainly how we work with it. So we're going to define a workflow from the input data. We want to get some output data, so we're going to try to find several intermediate steps to go from the input to the output. Okay. So if we look at a specific example, here we have it's H&E image. So that's the kind of image that are used by pathologists to grade cancer, for example. And if the goal is to segment the nuclei, we can start, for example, by a stain deconvolution. So we're going to extract what is purplish in this image from hematoxylin. Then we can filter the image to be less sensitive to noise, thresholding on the intensity, some morphological operation, and we end up with nuclei. Here we see that in that case, generally when you work in this context, you're going to have, two, three, a few images, generally just a few images. You're going to work a lot on one image to get the best results. You're going to test on the other images to see how it works. And if it works on all your images, you're going to be happy, and you're going to hope that it's going to work for all the images you have in your you have to process. Now, what's the difference with supervised machine learning? So here we talk about supervised machine learning. So we heard a lot about it with the previous presentation. Supervised machine learning means we have a training data set for which we know what we want to get. So in that case, we're going to have input data. So we use an algorithm, an existing algorithm most of the time. Some people develop new algorithms, but when you just want to train an algorithm, you're going to use one that you know is working well for your task. And then out of this algorithm, you're going to get some output data. As you have a training data set, meaning for each input data, you know what you should have, you can compare what you have as an output of your algorithm with what you should have. And so that's great because you can directly see if what you get is close or not to what you should have. And then you can actually change the algorithm, update your algorithm with some feedback to actually have something that is more like to what you should have. So in mathematical terms, you can compute an error between what you have and what you should get, and you're going to change your algorithm to minimize this error. And so you start like this, and when you're done with your training data set, hopefully you're going to get a trained algorithm that's going to be able to process your data. Okay, so if we look at a very simple example, but so the same example than before, but as an illustration, your training data set is going to be a set of images. And for each image, you might have, so maybe you have access to annotated data, or you manually annotate each single nucleus. And so then for each image, you can put the image into the algorithm. You can get this segmentation compared to what you should have, and then update your algorithm. And hopefully, at the end, you're going to get a trained algorithm that's going to be able to process any kind of data. Of course, this image has to be similar to the images in your training data set, and you'll be happy. So that's true for any kind of machine learning. So we're going to start with what we call classical machine learning, shadow machine learning. So when we use this for pixel classification, in this case, the goal is to actually be able to estimate a label at each pixel. That's why we call it as pixel classification. we're going to train a classifier that's going to be able to estimate a label that we call class at each pixel. So we're going to give example of classes, and then we're going to train the classifier, and hopefully we're going to obtain a classifier that is able to do what we want. So if we look at a simple example again, so here, I told you before, this kind of machine learning, it can be random forest. This is more like regression, but it's so that's not how all the algorithms work, but it's going to give you an idea about how it works with regression. So let's say here we have example. So each dot is a pixel, an example that was given by the user. So they are part of a training data set. For each pixel, we extracted 2 features. So now we're just going to say feature 1, feature 2, and we'll see what kind of features we can have. And so each dot is defined by 2 features, and you have the colors that correspond to the classes so that we define as a user. And we'll see how we can do it on an image very simply. So as you can see here, it seems that the dots that are in class 1, the blue dots, are more likely to be on the left part of the window, and so the dots of class 2, the orange dots, are more likely to be on the right. So we can try to estimate a curve that's going to separate our 2 classes like this. So we train a classifier that's going to be able to define a curve that best separate the 2 classes based on the features 1 and 2. So we see that it's not perfect. We can have some dots that are in class 1 that are on the right part, so within a set of class 2 dots. But overall, it's a pretty good decision. And now, if we have new dots corresponding to other pixels like this, we can plot them in this set, and we're going to have so we know feature 1, feature 2. And then depending on where they are, if they are on the left or the right part of the curve, we're going to be able to estimate a class for each of them. So the dots that are on the left are estimated to be class 1, and the dots that are on the right are estimated to be class 2. So basically, classical machine learning, that's how it works. A few tips that are very important when you use this kind of machine learning approaches is that you need to have what we call a balance for your classes. If you have more examples for one class than for another, then you're going to probably make some mistakes. So here, for example, we have just a few dots in class 2, more dots in class 1, probably do estimate a curve that looks like this. And then if we go back to the dots we had before, we're going to make some mistakes. Second thing that is really important is we don't want to what we call overfit our algorithm. So for example, if I give lots of examples, and especially lots of examples from the same that are from the same kind of images, we don't have very diverse data. So here I can always find a curve that's going to separate the 2 sets. So for example, this curve separates the 2 sets, class 1 and class 2, perfectly. But we see that it's not very generalizable. And when I have new example, probably that won't really apply well to my question, okay? So that's what we call overfitting. If we go back to good tips, is that first of all, we see that we need to select image features, and that's the most important part when you do this kind of machine learning. What are the image features that we can use? We can use features based on intensity, features based on structure, features based on texture, for example. The other thing that is really important is to have features at different resolution. So features that are high resolution at your pixel, for example, pixel resolution, but also features that are at a lower resolution, so corresponding to a smooth version of your image, like an average version of your image. This is really important because when you have a lower resolution, you're going to be able to take into account the context. When you want to segment your image, you need context. If you just have the intensity at your pixel, you won't be able to make a good decision. And if you want to understand what it is, just try to zoom in a lot on your images and try to understand what you are looking at. Most of the time you can't. You need to zoom out to have context. And that's exactly how it works with machine learning. So that's important to have image features, good image features that are suited to your problem at several resolutions. Then it's also important to annotate regions that are representative of what you're going to have in your images. And that's why it's important to have not one image, but several images. And hopefully images that are going to be representative of all the images you'll have to process. It's very important. Never annotate, sorry, that's the last one. Never annotate an entire region. Why is that? Because you're going to overfit. You're going to have lots of examples of the exact same thing. And so then you're going to be super good at evaluating, estimating for this very tiny region, but you're not going to be so good at generalizing your model. And that's why it's really important. And then try to define roughly the same amount of annotation for each class. How does that work on a real example? So here we have an image. So I used QPath. You can use QPath to do that. You can use ilastic. We saw that in the previous presentation. You can use LabKit in Fiji. And so here I have an image, a fluorescence image, where nuclei are stained in DAPI. So everything that is blue corresponds to nuclei. And epithelium is stained in white, and it's a cytoplasmic marker, so that's surrounding the cells. And here my goal is to segment epithelium, so the white region, stroma, so everywhere I have nuclei, and we see that sometimes it might be difficult because the density of nuclei is pretty low. And that background, so this is out of the tissue, this part is also out of the tissue. So let me start the video. Oh, yeah, I need to change that, and that should work, hopefully. Yes. So here you see I annotated one part of the epithelium, second part of the epithelium. I tried something very bright at the bottom, less bright at the top, several parts of stroma, and then background. And so can just do a few annotation, and then I can start to do a pixel classification. So this is here, it's actually a random forest. You can use the resolution, the base resolution. Then here I define the different features. So here, very important, I use 2 resolutions. And then I use the Gaussian, which is going to be the intensity more or less. And then the Laplacian of Gaussian to have structure. And you see that even with very few examples, you already have a pretty good, pretty decent segmentation. And then as it's super fast, you can add new annotation. It's going to be done interactively. And so you can add and try to get the best resolution. Here I'm missing some stroma, so I add some, I have a new result. So you see, these techniques are nice because as long as you just follow the few tips that are important, then very quickly you're going to have a good segmentation, especially if you're interested in some tissue. So in your case, I don't know in marines, depending on the images, but basically, if you want to have a pixel classification, so a label at each pixel, and you're not very demanding on the precision, it's going to be really good. Now, if you want to be more precise, probably it's going to be better to use deep learning method. So let's talk about deep learning. So why deep learning happened more like a little bit over than a decade ago? For 2 main reasons. First reason is the use of GPUs. So GPUs are graphic cards. So there were GPUs were designed at the end of the 90s for video games to render a 3D environment for video games because people were starting to use video games in 3D. So 3D environments, actually it needs a lot of computational power to do the rendering of all the small objects. But you don't need very complicated, it's not very complicated operation, mathematical operation. It's just tons of operation at once. And so constructors came with GPUs, which are similar to CPU, but you can do less complicated operation, but massively parallel. You're going to have, so nowadays, GPUs are hundreds, thousands of cores. While on your CPU, you have 2, 4, 8, 16 cores, maybe 32 max. So that's great because you can do lots of computation at once. And so this paper came out in 2011. So basically at early 2000, scientists thought that they could use GPUs to do scientific computation. And so in this paper, they show, for example, that with a GPU can go 60 times faster, and that's still true nowadays. It's from 50 to 100 times faster when you use a GPU compared to CPU. The other reason is that we had access to very large amounts of training data. So this is probably the most famous training data set came out in 2010 for a competition in computer vision. You have images for each image. Basically, you have a class that is associated. For example, this one, it's a dog. So you want to recognize object images. Here you have a car, here you have a baby, etc. In this data set, so ImageNet, for each class you have about 1,200,000 images for training, 50,000 for validation, and 150 for testing. So about 1.5 million images per class. And you have 1,000 different classes. So huge training data set. And with those two things, so deep learning could finally happen. So how does deep learning work? I'm going to try to give you a quick intuition. So basically, just to start with some vocabulary, with deep learning, you're going to have, so at least with neural networks, you're going to have an input layer corresponding to your input data, and an output layer where you have what you want to estimate. So in that case, we want to know if the input image corresponds to epithelium, stroma, or background. And then you're going to have hidden layers in between. So that's why we talk about deep learning. Here we have many layers. So we actually have a deep network, and that's why we call it deep learning. Then each circle here corresponds to a neuron, and that's why we talk about neural networks. So what happened in a neuron? So this is basically what is defined in your neuron. So you're going to have many different inputs here, x0, x1, x2, etc., coming from the previous layer here. And then for each input, we're going to apply a weight, W. So W0 to Wi. And so we're going to do the sum of these weights multiplied by the inputs. So we're going to have the sum of Wi xi. Generally, we add also a bias. And the output is going to be the activation of this equation. So if you know a little bit of math, you might have recognized here convolution. So that's why we talk about convolutional neural networks. And then we talk about neurons because there's an analogy with the natural neuron. So this is an artificial neuron. Each entry here, X, is actually similar to an axon from a previous neuron. Each weight we want to estimate is like a dendrite, okay? So the synapse to the dendrite, and then the output is compared to an axon. So that's why we talk about neuron. And the activation function is very important. So it's going to be, most of the time, the activation function is going to be equal to 0 if your sum is inferior to a certain threshold. For example, if it's inferior to 0, your output is going to be equal to 0. And then if it's superior to 0, it can be just the actual sum. In that case, you're using a ReLU, a rectified linear unit. So your output is going to be equal to 0 if this sum is inferior or equal to 0, and then it's going to be equal to the sum if it's superior to 0. This is extremely important because here, so mathematically, we are introducing nonlinearity. And if you don't understand that, it's all good. What you need to understand is that, sorry, if you don't have an activation function, you can have as many layers as you want. You will always be able to find a mathematical operation, extremely complicated, but there will always be a solution so that you can reduce all your layers in just one. As soon as you introduce nonlinearity with this activation function, even if you only have two layers, you cannot summarize these two layers in only one layer. And so that's an easy way to introduce complexity in your problem. So if you look at the end, we have very simple operation, and yet we can have very complex operation, and that's why it works for what we want to do. So how do we estimate our weights? Because here, that's what is important. We want to estimate those weights W's. Basically, we take the input and then we propagate to the first layer, that we propagate to the second layer, etc. So we do some sums. So this is just simple math. And at the end, we get a score for our output. So in that case, we have a score of 0.8 for epithelium, 0.3 for stroma, 0.1 for background. As I told you, here we do supervised learning, so we know what we should have. And I know that this image is part of the epithelium. So actually, I should have 1 for epithelium, 0 for stroma, and 0 for background. And that's great, because when you do math, now you can actually compute an error, which is going to be the difference between what you should have and what you have. So here I have an error of 0.2 for epithelium, minus 0.3 for stroma, minus 0.1 for background. And then we use what is called backpropagation to actually backpropagate this error. So we're going to backpropagate it to the last layer, and then we can actually compute an error in each neuron of the last layer, and then we can backpropagate again to the layer before, and so on and so on. And I'm not going to go into the details, but as the neurons, we can derive the neurons. Then if we have an error via some optimization during some gradient descent, then we're going to be able to slowly update the weights to actually minimize this error. And so we're going to go for the next image. So for example, here it's background. Again, we're going to have a score. We know what it should be. We can compute errors. We can backpropagate and update our weights, and so on and so on. So that's how it's done. But what are we actually doing? If we want to understand what the deep learning is doing here, actually what we do is that if we start from our image, I told you these are convolution. So we're going to convolve this image with many different convolution. And we're going to be able to extract some what we call low image features, okay, low-level image features. Now, if we combine all these convolution together in a new layer, so we convolve these low-level features together, then we're going to get some features of a higher level. Again, we combine all these convolution, and in the next layer, we combine them in some convolution. Now we're going to have image features of a higher level, and so on, and so on. And so that's really why deep learning is extremely powerful, is that we're going to actually have all these layers to estimate the best image features for the question we want to answer. And as we train this for this particular task, the image features that are estimated are really suited to our problem. And what is interesting here is that when compared to classical machine learning, is that for classical machine learning, we have to define the features. With deep learning, we actually estimate the best features. And so then that's why it's extremely powerful. Now, one thing that we need to understand is that if we want to know how many parameters we need to estimate, if I do just a 3x3 convolution with a bias, it's going to be 10 parameters per neuron. So if I look at my first layer, if I think that I have 32 neurons, it's going to be 320 parameters. Now, in the second layer, if I increase the number of neurons, I'm going to have 64 times the 320 parameters. So we're going to have over 20,000 parameters. And we see that at the end, we're going to have several million of parameters to estimate. So that's why we need GPUs. We need a lot of computation. That's why we need a lot of data as well, because if we have many different parameters, we're going to need a lot of data to estimate all of these parameters. One last thing that is not visible in this scheme is that generally we always also decrease the dimensionality of the image. So we start with the image. We're going to do a series of convolution, and for example, afterward, we're going to divide the image dimension in 2 on X and 2 on Y. So we're going to have an image that is 4 times smaller. And we're going to do it several times. This is really important because by doing that, at the beginning, we have convolution that only operate on small part of the image, but as we decrease the dimensionality of the image, at the end, we can take into account the whole context of the image. And as with machine learning, it's super important to take several resolution. With deep learning, it's also super important to take this into account. And so now I think it's time. So I wanted to show you a few examples, but it's all good because for the last session, Perrine Podvilotto will show you image classification and segmentation. So I'm just going to skip. We heard, so that was first paper in classification for cell mitosis. Then we had the UNet, just to show you that the previous image, we can then train a model to estimate stroma in epithelium, and that works fine. Then we had instance segmentation, that you'll see that. So I'm not going to talk about that. SAM, previous presentation as well. And so just to show you, I didn't have time, but some methods, fully unsupervised. And here it's really interesting because it's for instance segmentation. So for segmenting nuclei, so segmented objects, individual objects, this is a fully unsupervised method that is able to actually segment images. That's probably something that people are really looking into. And so just to conclude, deep learning has definitely revolutionized data analysis. Now we see that data is most important. If you remember the first slide when I show, classical programming, we work with a few images. Now we work with data, and the quality of the data, the curation of your training data set is going to be the most important. We have definitely a trend towards unsupervised deep learning, I just showed you. We also have a trend towards heavy computational foundation models. So SAM is a foundation model. What is a foundation model? The idea is that it's going to be a model that is trained on so much data, it's going to be super good. Large language models like ChatGPT or foundation models. The drawbacks is we see that we can try to interpret what's going on behind deep learning, but it's pretty difficult. Many people are working on it, but it's quite difficult. And something that we probably I just want to talk about it. So in previous presentation, we heard about carbon footprint of all these models. The foundation models are extremely greedy in energy. SAM, so we don't need to retrain it. We can use it. It's super performant. But even for inference, you need a GPU. If you don't have a GPU, it's not possible to use it. So that asks some question, because if you just want to segment a few objects in your image, you need a GPU. It's going to be the cost, the energy cost is going to be very high. Something also that we need to remember, I think, as scientists, SAM model is 10 billion parameters. ChatGPT is 100 billion parameters. And as scientists, we don't have the resources to train such models. Tech industry is training them. We don't have the resources, and that's also something we need to think about. We can use these models, but we cannot train them from scratch. So how do we evaluate those models? What do we do with these models? These models are wonderful, and we can definitely get something out of them, but we also have to put this in the conversation, I think. And with that, I will finish because I'm